Welcome and thank you for joining us for this webinar presentation. We are the Homeland Defense and Security Information Analysis Center, or HDIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. HDIAC serves as one of the premier information research partners and curators of technology advancements and trends for the Homeland Defense and Security community. As such, our organization supports those working in the Homeland Defense and Security domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the Homeland Defense and Security DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD Homeland Defense and Security research.
Good day, everyone. Thank you for joining this webinar presentation. My name is Philip Payne. I'm the technical lead for the Cybersecurity Information Systems Information Analysis Center. I am filling in today for John Clements, who's the technical lead of the Homeland Defense and Security Information Analysis Center. Before we get started, I would like to note a couple of administrative items. First, if you're dialed in by phone and would like a copy of the slides, they were posted to the HDIAC webinar announcement. You can go to hdiac.org/webinars and find today's webinar. When you click on it at the bottom of the announcement, it will say download presentation. Second, all participants are muted, but feel free to chat using the attendee chat window on the lower right-hand side of the webinar screen. You can use that to chat with each other, and I'll be monitoring that chat as well. However, if you'd like to pose a question for the Q&A session at the end, please click the 3 dots labeled more/panel options to bring up the Q&A window as part of your layout. At the end of the presentation, I'll go over the Q&A. For the benefit of those on the phone, I'll read the questions out loud to the presenter. If you have any technical issues during the presentation, have no fear. The full presentation will be available online. Please check back to the HDIAC website once the webinar is posted. The Go To Webinar button will take you to the YouTube link. With that said, I would like to introduce today's presenter. Dr. Jeff Fogg is the Engineer Operations and Environmental Chief in the Directorate of Logistics and Engineering at North American Aerospace Defense Command in the United States Northern Command with science and technology, environmental, homeland defense, and defense support to civil authorities included in his portfolio. Dr. Fogg has 32 years of civil engineering design, operations, public works, construction management, environmental compliance, hospital life safety, critical infrastructure, and homeland security defense, education, and research experience. For the past year, he has been a key member of the More Situational Awareness for Industrial Control Systems team, communicating the importance of cyber protection of critical infrastructure for our nation. He holds a BS, ME, and PhD in civil engineering, a graduate certificate in homeland defense, and professional engineer licensure in Colorado as well as Florida. Dr. Fogg?
Hey, thanks so much, Phil. I appreciate it. Can you see my slides?
Yep.
Excellent. So I'm Jeff Fogg, and today I'd like to discuss U.S. Northcom perspectives on nuclear energy. As part of this discussion, we'll look at what is unique about our military use cases and how we see nuclear energy as a technology enabler for future energy intensive capabilities. We recognize that existing fuel and power supply chains are at risk during production, bulk movement, and distribution, and used with growing exposure to kinetic, cyber, political, economic, and severe weather threats. Most permanent military installations and the defense critical infrastructure depends on commercial energy generation and distribution, which means we share the risk of grid dependency, which is essential to training, operating, deploying, and sustaining forces worldwide. From the NORTHCOM area of responsibility, and we are the global hub for our military capability. In remote operating locations like the high north or Indo-Pacific, we face the tyranny of distance, severe climates, and the potential for determined adversaries. We tend to group these concepts under the umbrella of contested logistics because regular delivery of fuel to these locations will either be contested by interdiction of long supply lines or restricted delivery time windows. Think like Arctic sea ice and how it constrains the delivery systems, which challenge sustained operations for us. Operational energy demands are expected to increase with directed energy weapons, radars, electronic warfare, and electrification of our combatant vehicles. So those are some of the things that we face out there in the future. And that really sets the groundwork for this presentation. So when we look here at energy dominance enables the warfighters of the future in defense of the homelands. So that's crucial to us and enabling our future capabilities. I'm going to cover a little interesting nuclear history that dates back a little while for us, and then pivot over to the conversation about reactor sizes, types, and fuels, and then wrap things up with some potential military use cases that are likely in the future. So when we look back here, and this dates back a little bit, and maybe some of you recognize some of these photos, but we started this nuclear journey with two pathways. On the left, light water reactor. On the right, the molten salt reactor. Light water reactors won out with Admiral Rickover leading development as the father of the nuclear navy for over 3 decades. So that was the real core of where we went. Molten salt didn't do so well. While inherently safer, molten salt lost out early due to the corrosive nature of the materials and salt impurities. So a technology that was a little ahead of its time as far as our material science capabilities in that era. And recognize this is in the late 50s, so this as far as the time when it goes. So outside of the light water reactor development with the Navy, we had other development from mobile nuclear power, and it's not a new thing, with the Army. The Army sled the 330-ton, quote, portable reactor PM-2A to Camp Century, roughly 100 miles east of Thule Air Base, now Patuxent Space Base, in 1960. That's 64 years ago. So you can see this is not new technology. Project Iceworm and Camp Century was an ambitious program to develop a military installation under the ice in Greenland. And for those of you who are unaware of the program, I suggest you take a look it up on YouTube for reviewing pleasure. It's actually a pretty fascinating little program. It's about a 30-minute video, definitely worth the watch, and just to kind of for a historical perspective. And if you ever find yourself at CREL, the Cold Regions Research and Engineering Lab up in Hanover, New Hampshire, they have a map of Camp Century as it was built back in the day. So it's interesting little bit of history. But we had a reactor in that location. And that reactor, a reactor PM-2A, was number 3 of 8 Army constructed reactors. And in October of 1960, PM-2A was started, and it immediately started leaking radiation. Additional shielding was fabricated on site to maintain operations, and the reactor ran for 3 years and was ultimately replaced in 1963 with diesel generation. And the reactor core was shipped back to the United States for disposal, and the nuclear waste, some of it was left under the ice. Now that reactor, interestingly, was highly radioactive when it came back to the U.S. So these experiments, as they were going in that time frame, were that. This was the first use cases, and it was a learning curve associated with those things. Camp Century was abandoned in 65, closed in 66 due to ice movement, and who knew at the time that the entire ice sheet of Greenland was constantly moving. And then in 65, the Army also abandoned the portable reactor program. So pretty historical moments, and you can see that time when we're almost coming up on 60 years since it was abandoned, and now we're re-engaging. So when we look at some of the failures in the public perception, again, the Army abandoned the portable reactor program in 65, but commercial reactors went on to great success with some notable exceptions. And here's some of the notable exceptions. In 1979, 3 Mile Island, brand new facility. And that really eroded the American confidence in nuclear power due to a mechanical and system failure and an operator error, which resulted in the release at 3 Mile Island and that just happened to coincide within 12 days of the theatrical release of the movie, The China Syndrome. So here we have a nuclear incident and a movie that releases 12 days before the incident, and it's just kind of an unfortunate event how they coincided. And then in 1986, 7 years later, Chernobyl had a massive failure through poor technology, poor design, and also human error. And those kind of things framed how we view nuclear power in a lot of ways. So it started developing baggage associated with it. So if you have a chance, actually, I'd highly recommend the HBO series on Chernobyl. It's very interesting. I thought it was excellent. But this drove, these events drove some of that anti-nuclear sentiment. And then more recently in 2011, Fukushima failed, the result of the largest ever recorded in Japan 9.1 magnitude undersea earthquake and resulting tsunami that knocked out the backup power and cooling systems, causing a partial meltdown. So again, overall, society has a lot of fear-induced nuclear baggage that has resulted in communities declaring themselves nuclear-free zones, resulting in excessive regulation and placed on nuclear energy, and the investments in nuclear technology waned in this window of time. So we'll see that now. We do see some lessening of these restrictions with newer types of energy that are out there. So we are fear-induced and with some understanding, but it has had an impact on how things have moved forward. What we've seen is that that shift in more safety was a renewed interest in molten salt. So it goes back to that. And we've seen some other things that have happened. While light water reactors continue to move forward in Rickover's nuclear navy with great success, what happened to molten salt reactors? Well, I wanted to close the loop on this real quick. And molten salt had a few advantages over light water. Molten salt is simpler and safer, has the potential to recycle waste fuel from larger reactor systems, and the salt ions can be harvested from the reactor, have medical applications for cancer treatment. So there are some unique benefits to molten salt in addition to producing energy. But the corrosion remains the huge challenge. Fortunately, we've had some advancements in material science over the past 60 years with respect to reactor materials and the salts. And that'll likely result in a reinvestigation in molten salt reactor technologies, and we're likely to see some more investment in these areas as time wears on. And we've already seen molten salt underway as a qualified fuel form for nuclear fuels. So there's movement in this area. Still way behind light water reactors, and not really the focus of DoD, but it is another area that will likely be explored in the near future. So when we start talking about the nuclear, and I'm shifting gears a little bit because we've talked about a little of the history of the two different types of systems we have, light water reactors, molten salt reactors, and then now where we're at as far as the production scale. So a little history and then where we're going. So talk about the reactor sizes. Not all reactor sizes are the same. Not all reactors are the same. You can see the big difference if you start looking at the kilowatt requirements versus megawatts and gigawatts as far as how much energy they're producing. That also correlates into how large the reactors are. So if you think of these reactors, we have a project that's called Valkyrie, which is an amps generator size reactor, 60 kW, 40 to 60 kWs in that range, small trailer mounted, small truck mounted, or skid mounted, something that is a very manageable, smaller size. Then we get up to a payload size reactor. And this is multiple containers, say 4 20-foot containers in that range, air transportable, but takes longer to set up, takes longer to pull down and disassemble and cool off specifically. And then we start moving up to the small modular reactors, where they're portable is a loose term, such that they can be moved, but they're unlikely to be relocated because they're going to be hot and the cool off time is going to be significant to enable movement, and how they're going to be broken apart. And this really, that small modular reactor, the 200 to 300 megawatt range, 20 to 300 megawatt range, is probably the extent of the DoD interest for things that could be operational on an installation. And that's if you factor in things like the potential for future synthetic fuel generation, directed energy, other really intensive, energy-intensive items that might be out there. So that's probably the DoD range of small modular reactors as far as the high end. But on the other side of that is we have the large-scale commercial reactors in the 1 gigawatt range. And we are interested in those also, just from a perspective of, is that's who we're likely to buy power from in the future, is that commercial sector. Most of our, 20% of our energy comes from the 20% of our commercial energy comes from nuclear power, and it has for the past 20 or so years. And what we see is those renewables that are coming in there, and we don't have enough renewables and that are going to make up that difference as far as they're just keeping up with current demand. And we need more investment in nuclear to get us ahead of the game, if you will. Because if you look at our average nuclear power plant is 40 years old, dating back to 1969 is the oldest one currently underway. The newest one was finished in Georgia in 2023. Previous to that was Tennessee in 2016. And then there's a 20-year gap where there was no new nuclear power brought online for 20 years. And that's where we really missed an opportunity. And so continuing to invest in nuclear energy in this large scale will be critical for our grid and independence, energy independence in the future. So switching gears again here, we're going to talk about what shifted. What shifted here is TRISO fuels recently, and I'd say recently because recently with the Pele program. The Pele reactor program is a 1 megawatt-ish sized reactor with also a thermal component. But this new fuel packaging for TRISO fuel is where we really enhance the safety aspect of nuclear energy. Tri-structural isotropic particle, TRISO, is a paradigm shift for safer nuclear future. And I apologize for the eye chart here because I know the print's pretty small, but these the TRISO fuel kernels are less than 1 millimeter in diameter, and they're incredibly robust. So you can see that the nuclear material is at the center there in red, and then you have all these layers that are built up around it, and that's what encapsulates it and makes it safe. This cannot be weaponized. These layers cannot be broken off of that fuel kernel, and if it was, if they were loose on the ground, they pose no more hazard than other nuclear materials that are used in nuclear densitometers or medical equipment that we have out there. So you can't do much with this that would have a big impact. So it can't be, like I mentioned, really weaponized. TRISO is a qualified fuel form and will be used in the Pele and Valkyrie reactors. So it's a great product out there. Our challenge here is to continue production of it and continue developing that capability in the future. So when we talk about TRISO fuels, I want to talk about one of the biggest benefits here, and that's the fuel savings aspect of things. So nuclear energy, one of the drivers here is cost. So how do you make this cost competitive versus diesel? It's from an energy generation standpoint. And I'm looking at it from a DoD perspective because we haul diesel wherever we need energy, and we have generators, and that's how we power our capabilities when we're forward deployed, or even when we have permanent fixed locations that are remote and austere. But the cost-benefit relationship is crucial to make nuclear energy more competitive in the future. And if we just go on cost alone, so if we use Pele, for example, in the 1 megawatt range, we'd be able to offset 2.4 million gallons of diesel over a 3-year TRISO-fueled reactor lifespan. So if fuel is $4 a gallon for diesel, then that would make this cost competitive, purely cost competitive at roughly $10 million for a reactor. If fuel comes up to some of our more contested, or I should say more difficult locations to operate from, where fuel costs are probably closer to $16 a gallon, that makes reactors competitive at the $40 million range. So you can see how what I'm driving at here is that these types of reactors provide the greatest economic value at locations where fuel costs are high. When TRISO fuel or other fuels can be manufactured at greater scale, these types of reactors will become more broadly competitive to a much larger market. Now, if you factor in things like human life, combat, like the loss of lives during fuel convoys in Afghanistan, TRISO immediately wins because we lost a lot of people in Afghanistan that were just hauling fuel, and all of those, and what you see there on the lower right-hand side is each one of those is a tractor trailer of fuel that's being hauled. And you can imagine all the convoys that are associated with that. And if you take all those out of the equation, that's a lot of lives saved. And that's one of our big driving forces here with this effort. So here's a schematic of the Pele system. I mentioned this earlier. The reactor is on the left-hand side. It goes from the reactor to the heat exchanger, and then it goes over to the hot turbine, basically the turbine that's generating the energy, the power, if you will, and then the power goes off to the blue line goes off to the equipment or whatever it's powering up. And then the lower right-hand side there is the control system where you're controlling potentially multiple reactors simultaneously in this type of system, because it's not just one; it has the ability to control multiples, and that would be and you can see the container size here. So this is roughly 4 20-foot containers, and this is a conceptual schematic of how things would work to give you an idea for Pele. Now, if you take that same construct, and you can see the size of that, and you go over to Valkyrie, and you can see Valkyrie is a much more compact program. Valkyrie is 40 to 60 kW versus Pele, which is in the 1 megawatt range. So much smaller, much more like a smaller standoff distance around the outside of the reactor. And an overall energy output 40 to 60 kW versus 1 megawatt, and all the components are encompassed in this one small space. And this would run an estimated 5 years unrefueled. So still significant savings associated with this type of system. A great potential operational point, and across a broad scale. And it gets down to this autonomous operations of very small reactors that have that ability to be forward deployed. Again, this would be truck mountable, skid mountable, like you'd see in this configuration that you could deploy in the field. So it comes down to the use cases. What are we going to look at the potential Pele and Valkyrie use cases? First, we need to look at the locations where the fuel costs are extremely high. And we have to look at things that are maybe under construction or that would be under construction, or we're going to recapitalize a cost. So how do you say if I was looking at a site and it had exceeded its lifespan, its operational lifespan, but it's still a run to failure type situation. This is a better use case for something like nuclear, because I'm not reinvesting in new generators or new fuel storage or other logistics methodologies where I'd have to support this type of capability or an older diesel technology. So you're looking for use cases where fuel costs are high, you're trying to avoid infrastructure development costs, and we need high emission assurance. So those are the kind of things that I'm looking for when I look at a new small reactor use case. So what comes to mind almost immediately would be the Arctic, remote North warning radar sites, and these seem like plausible locations, especially as they were in the process of being recapitalized. And if I look at a little further, I would think about Indo-PACOM and islands that have long supply routes, where these supply routes could be easily contested via adversaries and or extreme weather. I think that those are really viable locations for how you would employ this type of nuclear technology into the future. And because, again, costs are high, and as far as fuel costs go, infrastructure costs are very high for new development, and then you want high emission assurance in these locations. So when you go out of those extremely contested locations, you start getting to this competitiveness of cost. We get into also the mission assurance aspect of things. So we know that most every site already has commercial power that's being supplied from a mission assurance standpoint, but could small nuclear be a backup energy source in lieu of diesel? Or could small nuclear in conjunction with batteries be a backup energy source that could extend the runtime as we try to get to longer, higher reliability, such that when you switch power over from one system to another, a commercial to an islanded system, that you have that higher resilience, energy resilience, if you will, and the higher reliability. So how does that look? How do future missions look? Now, what are our requirements for future missions, and how could this enable those future capabilities? So, and we need to characterize that in the future with respect to the installations and the defense critical infrastructure. Don't limit ourselves to the installation itself, but start thinking about the entire supply chain, enabling key facilities that go outside the military installation and look broader across the whole DCI. Then we start getting to the idea of disaster response. So what do we do for disaster response? If we look back, one deployment of a Pele reactor, for example, 4 containers could save millions of gallons of diesel that would take thousands of shipments. And when you start looking at a place like Puerto Rico, for example, post Hurricane Maria or more recently post Hurricane Fiona, this is the kind of system that, if in place or brought in immediately thereafter, it could have put them back up online and started supplying power to key facilities very rapidly, where we don't have to worry about the continued delivery of fuel, the continued generator operations. It's not an inexpensive solution, but could be a very readily available solution that takes out a lot of the other logistics considerations once it's in place. And it all boils down to this cost-benefit analysis. Where are you getting the most bang and the biggest bang for your buck? And what do you value most? So those are the kinds of things that need to be factored into this type of employment in the future for small reactors. So let's hop over and look at some of the small nuclear reactor benefits. I mentioned this a little bit. The off-grid energy generation and remote distribution, like a Maria response or like a Fiona response, is that we would develop outstanding resilience, because this would be, or if it's look at other mission assurance capabilities, it would be off-grid energy generation and remote distribution. So you can get into areas that are difficult to bring commercial power into and provide outstanding resilience to these locations, because again, it's a 3-year runtime without being refueled, and that's 24/7 highly reliable nuclear energy. Also associated with this, that we should start thinking about things like energy and thermal generation. It's super interesting because nuclear power or these types of systems like Pele bring the capability to provide energy, but they also bring the capability to provide heat. So that heat could be used as a thermal component for a community, or it could be used for things like desalination or synthetic fuels generation. So generically, you can use an all-purpose reactor with that basically energy or power generation type capability to do multiple things. Or you could optimize your reactor design to focus on thermal and maximize specific capabilities like synthetic fuel generation or water desalination for carbon sequestration. So there's things that you could kind of tailor your reactor capabilities for these small reactors to do specific things as needed. Energy being the premium, but other capabilities are also there too. So with energy dominance, this is something to think about also, is that I could link together multiple types of energy intensive systems to create some very creative capabilities that leverage energy, future domain awareness, think radars, and directed energy weapons for defense of the homeland. So when you start thinking about how energy is a key enabler, is that energy is what you're going to leverage to have these other capabilities that you desire. And needless to say, when you employ this type of technology, you dramatically reduce logistics with fuel no longer becoming the long pole in the logistics tent. We eliminate that in those thousands of deliveries. These smaller reactors will have the advantage of scaled factory assembly line production versus on-site long-term construction. And these will be transportable systems that can start up quickly, but will still have to cool down before relocation. And in some cases, that cool down time, especially when you look at that 20 to 300 megawatt range, that cool down time may be too long, and those may be fixed facilities, but they would be portable, air quotes, but fixed. So I wanted to, I'm almost done, so thanks for bearing with me. But I wanted to call out some of our great partners that we've had in these efforts. And we have multiple efforts that are going on simultaneously in the nuclear space with great, outstanding partners, just fantastic, and pursue these, the same goals. But so we're all in lockstep of how we're moving forward with these areas. And the Marine Corps, Operational Energy Capability Improvement Fund, OECIF, the Office of the Chief Engineer, NASA, Idaho National Labs, MITRE, and Los Alamos have all been great partners in this space as far as nuclear energy production and how we're leaning forward to in this spaces. And lastly, I'd just like to say at NORTHCOM, we know that energy dominance will enable the warfighters of the future in defense of the homelands, and really that's all I have. So I'm not a nuclear engineer, so it'll be too easy to play stump the dummy. So please be kind, and I'll be happy to answer questions from the chat as they've popped up. And if you need to, I'll leave this slide up for a while, so you can always reach out to me, shoot me an email, and we'll chat, and or give me a call, and we can chat and thanks so much for letting me have the opportunity to present today. I really do appreciate it, and I look forward to your questions. Thanks.
Dr. Fogg, thank you. It was a great presentation. We do have a couple of questions in the chat, but feel free to put those in there as they come up because the Q&A session is now open. But our first question comes from Paul. He says, how do the severities of the 3 fear incidents compare?
So of the 3 incidents, it's interesting looking back in time. If I were to rate them, I would say that Chernobyl probably and there's actually, if you can do a little Google search, and there's actually 6 key incidents, and all of these rate in the top 6. There are a couple others that were also spill incidents that occurred, but to note that, and I bring this up because of there's this reticence towards nuclear energy, is that in the United States, when you look at nuclear energy, and you have to think about, well, how many people die in coal production every year? How many people die falling off wind turbines every year? How many people die from solar panel installation every year? And how many people die from nuclear every year or have died? And the nuclear answer is near 0. But there's death attributed to all those other sectors on a regular basis. So it's the fear is not, and that's in the U.S. The fear is not entirely factual. It's an emotional issue of how we perceive things and but when something goes wrong, it goes wrong in the fact that we close areas down. So if I were to rate them of those 3 incidents of worst to least bad, if you will, I'd say Chernobyl worst, Fukushima next worst, and then 3 Mile Island 3rd worst. However, Chernobyl bad because bad technology, bad design, bad big human error, all those things. Fukushima, unprecedented natural disaster. That was way outside the thought process of how bad things could be, and multiple disasters too, with the 9.1 earthquake and the 14-meter tsunami that came with it. So incredible event. And then and 3 Mile Island, I'm not sure how best to characterize that. Again, no loss of human life, just bad timing, and you know, as far as we were in the middle of the oil crisis event, but it does still rate in the top 6. So I hope that helps answer the question.
Thank you. Thank you for the thorough response. I guess it's just a follow-up question for myself personally. I'm a cyber guy, so pardon my ignorance, but when you speak of the fear from, I guess, from an individual standpoint, I guess this is not something that's obviously being marketed to individual domestic homes and things like that, but how, from a messaging standpoint, are we kind of counteracting the fear that the public towards nuclear energy at a whole? I know that's a loaded question.
No, I think it's a good question because I talked to my boss here about this, and we have this. She points out to me. She says, you know, we have as in our age group, and you know, as middle-aged adults, like probably most of the people on the line are, and middle-aged, I'll say anyone from 40 to 60. It's interesting. We have a lot of fear, a lot of baggage associated with things because of what we perceived in the past, and the things like how it's presented in the media and all those things. So, but as younger generations come along, that fear is not there. They're not carrying the same baggage. So the messaging for nuclear is really important as far as how this progresses forward into the future. And you know, we, a lot of times with society, we don't let logic run things. We let emotion run things. And so when emotion runs a topic, it takes us off track sometimes. So in this case, I think, you know, my perception is that emotion ran us off course, and so that's why we had a 20-year span there where there was no new reactors brought online. So it's a, you know, that's my personal belief or thought, and when I look at the whole writ large program, because if we continued to make the investments that we made before, we'd say, hey, 3 Mile Island, we blew it there. How do we make this better? How do we How do we recover from this, and how do we continue to move forward in a positive space and continue to build these reactors? I think that our reliance on coal and fossil fuels would be far less than it is now had we continued to make significant reactor investments. So I think we're starting to figure that out, and we're putting some of that baggage behind us. And I'm hopeful that in that 20% of power that we've been providing for the last 20 plus years, that will hopefully increase, because we need nuclear energy going forward, because we cannot keep up with the demand with just other renewables that are out there. And nuclear is I would call it a pseudo renewable, and it has the carbon footprint is much lower than coal, oil, natural gas, those types of other types of energy generation.
Perfect, thank you. Our next question from Paul: do any indicated reactor sizes compare with thermocouple reactors used in spaceflight?
So these would all be, so when you're talking about, I probably need a little more clarity here, and I don't have my NASA friends on the phone to do phone a friend. So I can't really answer that question, but if you shoot me that as an email, I'll get you an answer. I know that some of the spaceflight power programs for actual using nuclear for an energy source are out there, but I'm not aware of what the energy generation quantity is with that. The Valkyrie reactor is also looking is a reactor that's being designed in mind with future surface fission power. So that is, and NASA is one of our partners in that program, and so that would be the reactor type, size, scope, scale, and that 40 to 16 kilowatts. So that's a very small reactor that would possibly be in a lunar application in the future.
Thanks. Our next question from Scott: did you define cool down, quote unquote? Is it radioactive, quote unquote, hot that is cooling?
It's a radioactive hot that's cooling. Yeah, so it takes time for and there's another question in there, in that 20 to 300 megawatt reactor following 100% power history. Yeah, so once you empower them, when they're cold, moving them around is not a challenge. It's easy, relatively speaking. When they're hot, it's a big challenge. So how long do you let it sit? How long can you how long you can reasonably relocate it or move it? And so initially our thoughts were that some of these, and what also depends on like how long it's been running too, because the longer it runs, the longer the cool down is going to be. So these are some of the things that we can make some estimates on, but we don't have hard facts on how long this is going to be. And so when we look at these new small reactors, these are some of the logistics things we have to figure out. It's like, how long is it going to have to sit before it cools down? We can model it, but we won't know until we know. And so we'll model it, we'll come up with some best estimates, and it varies for each reactor design, how long it's been running. There's a lot of factors that are associated with that. So, but right now, there's nothing that we have in the plan that you can just flip the switch and turn it off and move it. It's going to take there is some cool down associated with that.
Great. Our next question from Kimberly: you commented that the small reactors were good for 5 years. How do you dispose of the nuclear component?
So what would happen is with the reactors is that these they would go back to like a depot level maintenance. So you would take that reactor, you would pull it off to the side, you would plug a new one in its place, and that reactor was off the side would cool down for a bit of time, and then you would relocate it back to the depot level, and they would take the segments they needed out, and they would refuel it, and they'd send it back out to the field again. So that's the kind of the operational concept for these reactors. Some of them have a very elegant plug and play type concept. Some are less elegant, but that's basically the concept. So the reactor component itself is what would be the part that would be relocated. A new one would plug in its place, and then you would, again, take it back for depot level maintenance.
Next question from Don: do you know how much Pele Valkyrie will end up costing?
No, but that's a question I ask all the time. So I look forward to, and that's why I framed it with that $10 million to $40 million estimate there, because Pele and Valkyrie initially will use TRISO fuels. TRISO fuel is an expensive fuel. There are other fuels that are out there that are far less expensive. So, but we need to get one over the finish line with existing fuel types first. But the fuel type will drive the overall cost of reactors. So we're still in this. And then we have the qualified fuel form issue. So we need to qualify more fuel forms out there, have different capabilities, and that will help drive pricing up or down. And so risk, so if it's a high risk location, you may want a TRISO fuel. If it's in a lower risk location, you could have a fuel that's a lot less expensive, but maybe it's not fully encapsulated. So there's a lot of things that are out there that will drive what the reactor pricing structure will be, and then the cost per generation. So that's, again, we're at the early stage of this. I hope to see these things online and up and running in my lifetime, and I hope to see them more broadly dispersed, but that cost structure will drive how broadly acceptable these things are in the future.
Next question from Graville. Many thanks for this informative presentation. Would it be feasible, the fabrication of a TRISO particle near the nanoscale range?
I have no idea, and I'm guessing possible. I just don't think there's much ambition or desire to do that at this point. There may be in the future, but you have to look at what would it be powering, and what would be the use case. So I just don't think right now that that's something that would be pursued, but in the future, I could see some possibilities there.
Okay, next question from Joel. Would such a reactor be used as a sole energy source for a semi-permanent base, ramping it up and down to meet load, or would they be paired with other generation assets?
So I think that you could put this at a permanent location, and again, nuclear. What's nice about it is that it does surge up and down to meet loads. So if that's the case, at the full tilt, with a payload reactor, maybe 3 years of operation, we think. But if the energy demand goes up and down like traditional power systems do, then you would probably get a greater lifespan out of the reactor, so it would run longer. Or you could pair with other, not generation assets necessarily, but other storage assets. So you could pair this with, or maybe if you had a peak load, you could pair it with a generator to get a peak load for a certain period of time. Or you can pair it with a battery. I always like the batteries, because batteries, they can, when the demand is down, the battery can always be filled, and so you can have a smaller energy production. But when you're off peak, it could be filling the battery, and then when you go on peak, the battery could be depleting, in addition to providing baseline nuclear power. So I think pairing with battery systems makes the most sense in the future, and I don't think that we've fully explored battery technology in this space as robustly as we need to, with especially for mission assurance applications. And I look at hospitals and critical infrastructure and DoD capabilities, where batteries with energy need to be a real key component of how we move forward in the future. Thanks.
Next question from Stephanie. Who in the DoD is performing studies on how small reactors will change or integrate with operations? Where might a developer go for funding on adapting their development for DoD applications?
Well, shoot me an email because we put together proposals quite a bit for that type of capability. So we're looking at all manner of things, and so we've had discussions with multiple reactor manufacturing companies, or potential manufacturing companies. A lot of people have concepts, not a lot of people have reactors. So I look at how I'm always interested in hearing what people's concepts are and what their use cases are, and how they think that it could be adapted to the military. I'd be happy to have that conversation.
Perfect. Next question from Christopher. Is investment being considered for small modular nuclear fusion reactor research in addition to fission?
Is investment being considered for small modular nuclear fusion? Not for us. So we're looking at the small modular reactors right now, and I'd say that our investment right now is in the Valkyrie and the Pele programs right now.
Okay, next question from Skip. Small reactor in combat conditions. What problem sets are considered now for recovery conditions from enemy control?
Yeah, so how I would look at this is, again, you kind of get into this challenge here of what could somebody else do with a reactor? They can't weaponize it. It would be like stealing a generator, basically, is how it would come down. It'd be a really good generator, but it'd be like stealing a generator. So you would enable, if you were at a forward deployed location, you would want to maintain very positive control over that. Is it the kind of thing you want to leave behind? Not ideally. So you'd want to go ahead and maybe in your forwardmost locations where you have a small use case, not necessarily, but we're at a location where you have a higher use case or a higher demand signal. Maybe that's the location you have it. Maybe it's not quite as far forward, or it's a more defensible location. So I wouldn't. I'm concerned about enemy capture, but I'm not overly concerned about it. Hope that helps.
Next question from Kimberly. How will you dispose of the spent fuel?
Yeah, we kind of covered that as far as how we would take it back and recycle it, or basically refit it at the depot level, and then from there, that spent fuel goes into traditional channels that we take care of spent fuel for existing reactors on the large gigawatt scale. So a lot of those are actually stored on site. The nice thing is that some of these fuels, when you start looking at different reactor configurations, you can actually recycle some of the spent fuel from large scale reactors to make the fuel for this type of reactor. So there's reactor fuel is really a fascinating topic area. I need to learn a lot more about it, but when you have smaller use cases like Pele, you're burning the fuel down much further than you would be with a large nuclear plant. So you're actually using up a lot more energy out of it, the bad energy too, which is a very positive thing.
Next question from Keith. How will nanotechnology affect design?
And when you scale it down to that nanotechnology, that would continue. So if you package down even smaller, you open up other use cases in those very small, much smaller devices. So the isotopes, there's unique energy capabilities in those. It's just what you're trying to empower. And so that's when you start looking at and then also when you go into the space applications, the amount of shielding that's out there, that drops off dramatically too. So there's a lot of unique capabilities that are out there, but it's not an area that I've been working in specifically because, like I said, this is really just easy to play stump the dummy. And I'd have to defer you to some of my NASA friends to get into that specific level of very small applications. Over.
And next question from Eric. What is the expected process for permitting these portable reactors? I'm asking about, say, the building permit or operating permit. I'm thinking about wind and solar and the permitting process that can take years. This delay would affect how it could be deployed.
Yeah, exactly. It is a long question. It is not an immediate process, and it's a function of the DoD has a kind of like the reactors that I showed you that were the portable ones that were used in Camp Century. The DoD has its own permitting process, so we have that component of things that we deal with. Now we follow the guidelines that are associated with Nuclear Regulatory Commission very closely, but it's our own process. when it goes to the commercial side, that's when those need to be followed more under their processing, under their permitting. So there's a separate entity, if you will, for DoD applications. Interestingly, this is a challenge that's come up with when we start looking at nuclear generation installations of who's going to run the nuclear generation. Is it going to be a commercial sector element, or is it going to be a uniformed or a military element that runs it? So these are some of the things that are challenging in the future. And you get into this regulation. There's also things with autonomous operations that are challenging. Can we operate nuclear reactors autonomously, or do they have to be fully manned 24/7? So it goes back to DOE, Nuclear Regulatory Commission, and how we want to control and ensure their capabilities in the future. So I think there's a lot of questions being answered there, but from the DoD side, it's much more immediate. From the public sector side, there's much more to be hashed out there.
Thanks. And I think the last question we have in the chat as of right now from Paul: how will the regulatory oversight from the NRC be applied to set up operation, dismantling, and disposal outside of CONUS?
Great question. I do not have the answer to that, because it's when you go outside of CONUS, and we're doing a look to see who would be who would be welcoming of this type of technology, and so we've kind of done we're doing a survey, if you will, and canvassing the audience globally to see who would be welcoming of this type of technology. So I think that there's some real positive impact as far as, are they going to say, hey, we're willing to accept whatever risk there might be because of the benefit, or not. So and that's part of, and actually even get down to the states of like which states even in the United States are willing to accept this type of risk, or how they perceive the risk. And what we've discovered is that a lot of it's education. And once people understand what these reactors and the capability of them are and how safe they are, that they recognize the risk is not as bad as they thought it was, because you're helping alleviate the load of that baggage. So you're saying, hey, here's how things are now. This is not 64 years ago. This is today. Here's where we've advanced. Here's how much safer these things are. Let's have the conversation here to understand the current technology, and then let's continue to move forward and say, is this the kind of technology you want? Is this kind of the capability that you want? Do you want to alleviate those 2.4 million gallons of fuel that you're going to have to haul in here somehow, some way? Or do you want to build the infrastructure and the storage tanks and the multiple generators and the fuel distribution system, and take the environmental risk associated with all that? So it's understanding the conversation, understanding what the current technology is, and really explaining that to the potential customers. And what we've found anecdotally is that once the customers understand, the customers are very receptive. So that's a real positive thing for nuclear energy in the future. And then I'll look at that last question here as the vehicle-borne IEDs. Yeah, and if this took a round, what they're doing with PALE is they're actually doing kinetic testing against the fuel. And again, it possibly could break apart the larger fuel element, but it would all go down to that 1 millimeter size kernel, and so it wouldn't break down any further than that. So the fallout effects would be near zero. It would be like a dirty bomb, and a dirty bomb, basically there's no fallout effect. It is just the dirty little pieces that fall on the ground. So I liken it to, I live in Colorado here, and we had somebody that was a construction worker who put a nuclear densitometer on the back of his pickup truck riding up the interstate. And that nuclear densitometer fell out of the back of the pickup truck and hit the ground at 60, 70 miles an hour and busted open and spread nuclear debris across the interstate. In effect, that was a dirty bomb. And they went out there and they discovered all the little pieces and picked them up off the ground, and life is good. That's about the effect that something like this would have in the worst possible case. So, thanks.
All right. I think that's all the questions that I see in the Q&A in the chat. So at this time, I would like to definitely extend our thanks to Dr. Fogg again. Great presentation. I learned a lot. I could tell that the topic was relevant based on the active Q&A and chat that we had. So with that said, please check back to the HDI website. The slides are up there and available for download as of right now. Within a day or two, we will also have the recording of this webinar, and the link will be posted to the same HDI webinar announcement, which will take you to the HDI YouTube page. Please feel free to contact Dr. Fogg directly He's kind enough to share his contact information, or reach out to the contact alias at HDI if you have any other questions or would like to see different topics related to our webinars. Please take time to answer our survey as well. And with that said, I'll end today's webinar. Thank you very much.
Thanks so much, everyone.